Lecture 24, Partial Differentiation. So partial derivative. The derivative of a function of a separate variable with respect to one of the independent variable regarding all other variable as a constant is called partial derivative of a function with respect to variable. Now if you take a function u is equal to xy means is a function of two variable x and y. Here x and y are two independent variable, and if you want to evaluate the differentiation of that function with respect to x here, so we write the partial derivative with respect to x, and it means y remains constant or say same, and we have to evaluate the change in x. So we write del u upon del x, or sometime we write u suffix x limit del x tends to 0 fx plus del x and comma y minus fxy divided by del x. So here we are just evaluating the change in x. So we write u suffix x or say del u upon del x, or sometime we write f suffix x. So it means is a partial derivative of u with respect to x. And similarly, if we want to evaluate the partial derivative with respect to y here, so we write del u upon del y. Here we are evaluating the change in y and x treating as a constant. So you have to remember del upon del x or del upon del y is a symbolic representation of a partial derivative, and this is represented by, if we write the function, so we write fx or sometime we write fy. So this is a simple representation of a partial derivative. So the partial derivative for the higher order, if suppose if fx fy or sometime we write u suffix x u suffix y exists, then these can be further differentiate partially with respect to x and y, as we write del u upon del x and of del u upon del x, or sometime we write del 2u upon del x2, and we write f xx. It means the 2 time partial derivative of u with respect to x. Similarly, if you want to differentiate f 2 time derivative of a function f with respect to y, so we write this is a 2 time partial derivative with respect to y, so we write f suffix yy, or we can say del 2u upon del y2, and this means this is a 2 time partial differentiation or derivative, 1 time with respect to x and 1 time with respect to y. So you have to remember fxy or we write fyx. So if we write fxy, it means first we take the derivative with respect to x, then we take the partial derivative with respect to y. And if we write fyx, so it means first we take the partial derivative of u with respect to y, then with respect to x here. And here you have to note it in journal, fxy is equal to fyx. Now we discuss some basic property of the partial differentiation or partial derivative. So suppose if we have two functions, suppose u is a function of x and y, and there's another function v is also a function phi xy, then if we have a function z is equal to u plus v, so we can say z is also function of x and y, and if we want to take a partial derivative of z with respect to x. So we write del z upon del x, and is directly operate, this is a linear property, so we can write del u upon del x plus del v upon del x. And if we want to write a partial derivative of z with respect to y, similarly we write del z upon del y, so we write del u upon del y plus del v upon del y. Now the second point, if z is equal to, we have the function z is multiple of these two functions. So again, z is a function of x and y. So if you want to take a partial derivative with respect to x here of z function, then we write del z upon del x is equal to, here we apply the product rule. So we write u as same and the partial derivative of v with respect to x, then v same and the partial derivative of u with respect to x. And similarly we can write for the y here. And the third property, if suppose z is a function such that is a u upon v, and we want to take a partial derivative with respect to x or y, then del z upon del x, here we apply the quotient rule, which is we write v square in denominator and v as it is the partial derivative of u with respect to x minus u the partial derivative of v with respect to x. And in similar manner, if we can take the partial derivative with respect to y here. So you have to remember, if the two functions in product, so we use as a product rule this one, and the if z is a in the form of quotient, so we apply the quotient rule. And if we have, suppose z is equal to function of u, we can say u, and u is a function of x and y. Suppose u is a function of x and y, and we want to take a partial derivative with respect to x here, then we just write del z upon del x. Now here we apply the chain rule. It means we take the partial derivative of z with respect to u, because z is a function of u and u is a function of x, so we write del u upon del x. So this is a partial differentiation of z with respect to x if z is a indirect function of x and y. Similarly, if we want to take a partial derivative with respect to y here, so we write del z upon del y. So we apply the chain rule here, del z upon del u into del u upon del y. Now by the help of example, I explain you how to take the partial derivative. So we have to find the first order partial derivative of that following function. So suppose we have a function u is equal to log x square plus y square. So first we take the partial differentiation with respect to x. So we write del u upon del x is equal to, so you know the derivative of log is what, 1 upon x square plus y square into the derivative of that function. Here we take y as a constant, we treat that y as a constant. So x square plus, this is, suppose this is a constant term, so we write the derivative of that term is what, so x square we get 2x and the derivative of y square is 0, so we write just 2x. So the partial derivative of that function with respect to x is 2x upon x square plus y square. You have to remember, in that case we're treating y as a constant. Now if you want to take a differentiation partial differentiation with respect to y here, so we treated x as a constant, so we write del u upon del y is 1 upon x square plus y square into the derivative of that function and treating x as a constant, so we write into 2y, so we write 2y upon x square plus y square. In that case we're treating y as a constant. Similarly, we have another function u is equal to ax square plus 2hxy plus by square. So if we take the partial differentiation or derivative with respect to x here, so we write del u upon del x, and in that case we're treating y as a constant, so here a is also constant, x square, so we write the derivative of x square is 2x into a plus, in that case the h and y is constant, so derivative of x is 1, so we write 2hy plus, now this term is what, constant, so derivative of constant is 0, so we get 2ax plus 2hy. So this is a partial differentiation with respect to x, and the similar way we can take the partial derivative with respect to y here, so we write del u upon del y is what, now treating x as a constant, so the first term is completely constant, we write 0 here, the derivative of y is 1, so we write 2hx, remember the x is constant here, now the derivative of by square is 2by, so the derivative with respect to y is 2hx plus 2by. So in that way we can find the partial differentiation of any function. Now the geometrical interpretation of a partial derivative. So suppose we have a function z is equal to x square minus y square. So here if we want to take a partial derivative of that function with respect to x at suppose a point origin that is 0 0. Now so what it mean, so we want to evaluate the partial derivative of that function, or we can say we have to evaluate the change in x while y remains constant. So what's the partial derivative of that function? As you know, the partial derivative of the function z with respect to x is 2x because y remains constant here. So if you want to explain geometrically, so for that I plot that particular function in 3D figure. So this is a 3D diagram of that particular function x square minus y square. Here this represent the y-axis and that represent the x-axis, and the surface is plotted along the z-axis. So here we have to evaluate the partial derivative with respect to x at 0 0, means at origin we get the partial derivative at origin, we get 0. 2 into 0 is 0. So what it means? So it means if we plot the x-axis, if you see that 2D diagram, so this is suppose x-axis and that is the z-axis, and that curve representing the z function. Now we have to evaluate the partial derivative at that point, that is origin. So it means we are taking the partial derivative with respect to x, it means a tangent is passing through that point. So here you see in that 3D diagram, that red line, this red line is representing the tangent line which is passing through the origin, or say at 0 0. So this is what, this is the, we can say the partial derivative which is passing through that particular point, that is origin. So but if we want to plot a different partial derivative of that particular function with respect to it at different point. So similarly, we can suppose we want to evaluate the partial derivative of x at says 0, 0, 2. So what it means? It means the tangent passing through that particular point means, but you have to remember here this is a tangent line which is passing through the origin or say 0, 0, and if you want to evaluate the partial derivative at 0, 2 at different point, so the tangent it is passing through the different at that particular different points. But because we are talking about the two-dimensional function, so we are not using the tangent, the word tangent line, we are using the tangent plane. So this is the plane which is representing the partial derivative of that function with respect to x at origin, and if it is at different point, so that plane is moving in that particular direction. As similar, if you want to partial derivative of the similar function that is equal to x square minus y square with respect to partial derivative with respect to y at, suppose now we are taking the different point says 2, 3 or 2. So what will happen? So you see, now this is, we take a y-axis and this is the z-axis and this is the curve. So we are taking the point the 2 and suppose here somewhere is 3. So it means a tangent which is passing through that point is a partial derivative of that function with respect to y at that particular point. So what we get here, the partial derivative of z is with respect to y is minus 2y, and at point 3, 2 we get minus 2 into 2, that is approximately 4. So the 3D, in 3D figure we can explain here, because in that case we are treating x as a constant, so the tangent is passing through that curve at that particular point, or we can say a tangent plane or cross section area as you see in that figure. So y as a constant and it change along the y-axis. So you have to remember the partial derivative, geometrically we can say a tangent plane passing through a particular point, and in this manner the partial derivative of any two-varied function is geometrically interpreted. Now take a one more example. Suppose u is equal to tan inverse x square plus y square upon xy. We have to take the partial differentiation with respect to x here. So del u upon del x, or we can write u suffix x also. So what's the derivative of tan inverse? As you know, 1 upon 1 plus x square plus y square upon x plus y whole square. You have to remember here we are treating y as a constant when we take the partial derivative with respect to x. Now take the derivative of that function. So the partial derivative of that function also. So what we get? We simplify that function, so you can write x plus y whole square 1 plus x square plus y square whole square, and the derivative of this, use the quotient rule here. So we write what? X square x plus y whole square x plus y, and the derivative of that function is what? With respect to x, so we write 2x and the y square is 0 minus, now x square plus y square, numerator same, and the derivative of denominator, so the derivative of x is 1 with respect to x and y is 0, so we write 1. And if you simplify that equation, so you can get x square plus 2xy minus y square upon x plus y whole square plus x square plus y square whole square something, right?